Hello everyone, how are you today? Let's take a look at assignment 55, graphing rationals. Okay, assignment 55, so I'm looking at something like this. Y equals 2x minus 5 and 3x plus 4. Okay, so one of the things that I love about transformation graphing is that it's so fast. There are just these consistent rules, and I can be done. Or remember graphing parabolas in assignment 40. Um, Regardless of what form they gave us, we could be done in 3, maybe 4 steps at the most. Well, graphing rationals also comes with a set of recommendations, um, but it does take a little longer because these graphs can be much more complex. By the way, that says y equals. I think I want to circle that space as kind of a dead space. All right. So here's what we're going to look for. We're going to look for an x-intercept. And an x-intercept, well, since Algebra 1, you've known that you could find an x-intercept by setting y equal to 0 and solving for x. So let's see what happens with that now. So first step, we learned in our Algebra Basics unit was when we have an equation with a fraction, let's multiply both sides by the denominator to clear out the fraction. What happens over here, though? That's right, 0 times all this stuff. What's that going to be? It's going to be 0. So before we go further and actually write down what the x-intercept is, what played a role in finding that x-intercept? Did the denominator play any role in deciding where the x-intercept was? No. Denominator canceled right out and became 0 on this side. It's only the numerator. Don't forget to add 5. And then divide by 2. So we know that the x-intercept is at 5 halves. And that's the first thing I want to find. I want to find that x-intercept. Okay. And 1 equals 2x minus 5 over 3x plus 4. So now what about y-intercept? Well, to find a y-intercept since Algebra 1, we've been saying set x equal to 0. So if I put zeros in these places, I'm going to have y equals which will be or negative 5/4. So our y-intercept, y equals negative 5/4. Okay. What's next? Well, do you remember our reference graph for rational functions? Way back in August. This was it. And the graph looked like this. And it came in pieces like this because these pieces were bending to these asymptotes. We got the chance of a horizontal asymptote, we have the chance of a vertical asymptote here. So let's talk about how to find those asymptotes. So a vertical asymptote is where the function is undefined, at least in the realm of rational functions. We'll have a more robust definition in calculus than this. But we know a function is undefined when a fraction has a denominator of 0. So if we want to find vertical asymptotes, we want to find when the denominator is equal to 0. So let's write that down. 3, vertical asymptote when denominator equals 0. 3x plus 4 equals 0. 3x equals negative 4. X equals negative 4/3. Nice. It is possible, yes, to have more than one vertical asymptote, and we will definitely explore that. Negative 4/3. Now, horizontal asymptotes, yeah, I think I'm going to go along with your Algebra 2 definition of horizontal asymptotes. There are three different ways to find, or three different types of horizontal asymptote. And they depend on comparing the degree of the numerator with the degree of the denominator. And I'm going to abbreviate these as d sub n and d sub d. Okay? We're going to compare these. And we're going to think about a horizontal asymptote as the long-term behavior of the function as x heads to infinity or negative infinity. Okay? So we're looking at the long-term behavior. So what happens if we put bigger and bigger and bigger and bigger and bigger numbers in here? Okay, so if I plug in 100,000, so look, if I've got 200,000 pizzas sitting on a table, except that they've miscounted and they're 5 short, and 300,000 people showed up to eat them. Well, you know, there were these 4 invited guests who showed up. What sort of amount of pizza would you be getting? What can we say about that? Well, you know, when you're talking about this many pizzas, you're really not going to notice these people showing up or that they didn't deliver these. It's certainly going to be the case if we make the numbers like this. Really, no one's going to notice the 5 missing pizzas or the 4 extra people. Instead, we're going to let these things go away. And now here, I've got this fraction. These numbers are the same. I can cancel them out. And so it appears to me that we're going to say that each of you is going to have approximately 2/3 of a pizza. Fabulous. So what I notice is that in this case, the degree of the numerator and the degree of the denominator are the same. And when they're the same, look what we did. We looked at the ratio of leading coefficients. 2/3 is our horizontal asymptote. So with horizontal asymptotes, if the degree of the numerator is equal to the degree of the denominator, then y equals the ratio of leading coefficients is the horizontal asymptote. So if I had 7x plus 1 and 4 minus 3x, again, the leading coefficients, that's a leading coefficient and that's a leading coefficient. It's not the numbers that are front. Coefficient is the number in front of that variable. These are our leading coefficients. And so y equals 7/-3 is going to be our horizontal asymptote. Remember, with the commutative property of addition that your middle school math teacher tried to share with you, you know, we could rewrite this like this, and then, yeah, there are our leading coefficients. It's -7/3. Okay, what happens if the degrees aren't the same? If the degree of the numerator is in fact smaller than the degree of the denominator? Well, we've already seen that in our reference graph, haven't we? this was that case. We had x to the first on the bottom and x to the 0 power, right? Because anything to the 0 power is 1. Well, almost anything to the 0 power is 1. So in this case, we've got degree of the top is smaller than the degree of the bottom. And in a situation like this, or, if we had 4x plus 5 over x squared plus 1, again here, the degree of the top is 1, the degree of the bottom is 2. When the degree of the top is smaller than the degree of the bottom, we're going to say that y equals 0 is our horizontal asymptote. Okay, and why is that? Well, there's some really good reasons for it, but they're outside of the scope and time I have in this video. So we're just going to go with y equals 0 is the horizontal asymptote. And then finally, if the degree of the numerator is actually bigger than the degree of the denominator, there is no horizontal asymptote. Oh, yay! No, sorry. Instead, we have a slant asymptote. So we're going to have to talk about how to find a slant asymptote. Yeah, slant asymptote. That'll be a thing. But for our problem here, to get back to things, where's our horizontal asymptote, number 4? Well, the degree here is 1, the degree here is 1, and so we're going to say horizontal asymptote is y equals 2/3. Ooh, look, a typo or a write-out. Remember, vertical asymptote is a vertical line, and so it has to be x equals a number, not y equals a number. Sorry if you found that confusing. Okay, so to review, we set the numerator equal to 0 to find the x-intercept. We set x equal to 0 to find the y-intercept. We set the denominator equal to 0 to find the vertical asymptote, and we looked at the degrees and leading coefficients to help us find horizontal asymptotes. Now, I don't know if you noticed this, but this is kind of a very nifty little graphic organizer concept here, where we can say, okay, look, I've got these ovals are everywhere I can have them except on the diagonals. The top finds the x-intercept, the bottom finds the vertical asymptote. This is the y-intercept, and this is what I look like to find the horizontal asymptote. Okay, so let's now, step 5, graph what you have and connect the dots. So we've got an x-intercept over here at 5/2, a y-intercept at -5/4, a vertical asymptote at -4/3, and a horizontal asymptote at y equals 2/3. Now, in my brain, I always think of the way the function behaves with respect to these asymptotes as though these were objects in space and these were gravity wells. I know, it's crazy. But look, after I connect these two, what happens next? Well, this one keeps going, but it bends to the gravity of that horizontal asymptote. And if we go the other direction, when we come out from this side, we have to bend to this asymptote now. And so we have something that looks like that. Okay? Actually, it'd be a little more like that. Okay. So we're bending to the asymptotes. This is what I mean by graph what you have and then connect the dots. So we connected our dots. We bent to the asymptotes, and we're not done yet because there's always something on either side of a vertical asymptote. That's not true about a horizontal asymptote. But it is true about vertical asymptotes. Let me say it again. There is always part of the function's graph on each side of a vertical asymptote. Not necessarily horizontal, but definitely vertical. So there's something over here. Does that something look like this? Sometimes it does. Does that something look like this? Usually it does, but not always. So I'm going to say that to figure out which one, rather than just saying they always do this and then getting it wrong, we're going to say, okay, this vertical asymptote here was negative 4/3. I want to choose a number to the left of negative 4/3, negative 2. And I'm going to plug a negative 2 into this function. What am I looking for? Well, I'm looking to know what the y value is at negative 2. Is the y value above our horizontal asymptote at 2/3? Or is our y value going to be below our horizontal asymptote at 2/3? Okay, so if I plug in a negative 2 here, I get negative 4 minus 5 is negative 9. And if I plug in a negative 2 here, I get negative 6 plus 4 is negative 2. Negative divided by negative, that's positive. Positive 4.5 is definitely bigger than 2/3. So negative 2 halves. Now, this is called, in our universe, a test point. I need you to graph a test point. That's number 6. I'm graphing a test point to see where the other part of the graph is. Also, I kind of knew it was going to be up there, but I wanted confirmation because if this was supposed to be the piece, then I would need another x-intercept here. But we only found one x-intercept, and it was over here in positive land. So this doesn't exist, which means my graph can't possibly be that piece down there. Okay? But please, don't make assumptions about them always, sort of going this way on the diagonal. It really doesn't happen all the time. And that's a favorite test question. So let's put down step 6. Step 6 was use test points as needed to complete the graph. I always prefer to use as few test points as possible. As few test points as possible. Now, I would love it if you would get to the place with your comfort in this, which is certainly not today, but I would love it if by the end of our little unit on this, you were comfortable saying, okay, x-intercept is at 5 halves because I set the top equal to 0. And y-intercept, because I covered up the x's, was negative 5/4. And the vertical asymptote, remember we get that by setting the bottom equal to 0, is negative 4/3. It's probably worth showing the work here because a lot of people write 3/4 here, or negative 3/4 here, or positive 4/3 here. Those little mistakes that you would catch if you actually set this equal to 0 and solve for x. And remember the horizontal asymptote, because the degrees are the same on top and bottom, we look at the ratio of leading coefficients. So our first step is to find all those things. Our next step is to graph what we know. Horizontal asymptote at y equals 2/3. X-intercept over here at 5 halves. Y-intercept at negative 5/4. Anything else? Oh, a vertical asymptote. There's a vertical asymptote at negative 4/3. Okay. So I'm going to connect the dots and bend to the asymptotes. Really, that connecting the dots helps a lot of people. But then I have to bend to the asymptote. And let's just look at the alternative, by the way, of what we've done here. I connect these points, and some people want to do that. It's possible that that can happen, but that's almost never. And what would tell me that was happening is I have another x-intercept here. Okay, so we're going to start paying attention to things like that. And over here, can I come back this way? No, because then I fail the vertical line test and I'm not a function anymore. So I have to be going this way, and I have to be going this way as a way of extending that connection between the things I know. Okay? Now, that's step 5 where we graph everything we know. And then finally, step 6 was that place where we said, okay, let's test a point. And we plugged a -2 into each of these, and we got -9 on top, and we got -2 on the bottom. And we said, well, 4.5 is definitely bigger than 2/3. And so we're up here at -2, 9/2. And so we got this, and we got this. There we go. Okay, so let's move on. Your turn. Would you please graph y equals 6 minus 5x over 4x plus 1. Pause the video, give this one a try, come back when you're done. Hi, welcome back. So we set the top equal to 0. To find, what was it again? That's right, that's our x-intercept. We set x is equal to 0, doink, to find the y-intercept. So my y-intercept is going to be 6 over 1, or 6. What about my vertical asymptote? Yep, when the function is undefined, that means the denominator is equal to 0. And so for our vertical asymptote, we have 4x plus 1 equals 0, or x equals -1/4. And finally, the horizontal asymptote. Well, remember, it's not 6 over 4. We want the leading coefficients when the degrees are the same. So I've got y equals -5/4. So let's graph the things we know. We know that we have vertical asymptote at -1/4. And look, please don't do this thing like where you say, well, that's 1, so that must be 1/4. So I'm going to be right over here, because you're just making it hard on yourself. Put the thing over here and just label it -1/4. Okay? Horizontal asymptote, -5/4. Y-intercept at 0, 6. And an x-intercept at 6/5, 0. Another reason to not make the little tick marks is so that we can have enough space to see things and to draw things. If you make this wicked close to this, it's going to be really hard for you to do anything but go straight up. And we know we're not going to go straight up, because once we connect those, we're going to bend to that asymptote and bend to that asymptote. But if I put this dotted line right over here, thinking that, well, if this distance is 1 and this distance is 1/2, then this distance must be 1/4. And so now you're drawing something silly like this, and you're saying, okay, little graph, you've got to go like that. And that's just really hard for our brains to process. So give it some room, let it breathe. Okay. And then we've graphed what we know. Step 6, use test points as needed. So my test points, okay, I want something over to the left of -1/4. There's something on either side of a vertical asymptote. So if I put in something like -1, -1 times -5 is 5, plus 6 is 11. And -1 times 4, sorry, there's a little 4 hidden here. That's -4 plus 1 is -3. And that's -11/3. Ooh, is it really? I think something's gone amiss. What could have happened? 4 times -1 was negative 4 plus 1 is negative 3. Yeah, I got that. And my horizontal asymptote was negative 5/4. Yeah, I got that. Negative 5/4, yes. My x-intercept is at 6 over 5. And when I plugged in that negative 1, I did get 11, and I did get negative 3. Well, so here's what I'm sort of feeling uncomfortable about. I'm expecting a number that's bigger than negative 5/4, but this is more than negative 3. Can that work? Yes, it can. It's down here. It's down here below this. This is negative 1.25. This is negative 3.66. So negative 3.66 is going to be below negative 1.25. And so that's where my test point lands me. Negative 1, negative 11/3. Yes, I do need you to label a test point over there. And there's our graph. Okay, we're going to pass through this point and bend to that asymptote and bend to that asymptote. Fabulous. Okay. Next. What happens if we have something like this? Y equals x plus 1 over x squared minus 4. Now, this is different because, that's right, we've got this higher degree in the bottom than we do in the top. So we already know that the horizontal asymptote, because the degree up here is 1 and the degree down here is 2, when the degree of the numerator is smaller than the degree of the denominator, that's when we have y equals 0. Cool. What about x-intercept? Well, we set the top equal to 0. That gives us x equals negative 1. Y-intercept, we set x equal to 0, so that gives me negative 1/4. And the only thing we still need is the vertical asymptote. Oh, look. X squared minus 4 equals 0. X squared equals 4. And what am I supposed to remember when I take the square root of both sides? Yeah, that plus and minus. So, I've got two vertical asymptotes. Now, what's this going to look like? We've got a vertical asymptote over here at x equals 2. We've got a vertical asymptote over here at x equals negative 2. We have an x-intercept at negative 1. We have a y-intercept at negative 1/4. Now, and horizontal asymptote y equals 0. Behold, please notice this. See that? That's me crossing a horizontal asymptote. Now, there's some situations where, I can cross a horizontal asymptote with rational functions. With rational functions, that's possible. With exponential functions, our next unit, no, we're never going to cross a horizontal asymptote. And we never, ever, ever cross a vertical asymptote, because a vertical asymptote is a place where the function is undefined. Therefore, there can't be a point on our graph on a vertical asymptote. But a horizontal asymptote describes the long-term behavior of the function as x heads to infinity, where the function value is headed, as x heads to negative infinity, where the function value is headed at. Okay, so we'll get to those wings in a little bit. Right now, though, in between two vertical asymptotes, well, this is actually kind of convenient, because in between two vertical asymptotes, I can have these four options, and only these four options. So when you're looking in here between these two vertical asymptotes, you know that you've only got these four choices. Ready? I wonder if they look familiar to you. That's right. Our basic even or odd degree polynomial shapes. Now, these are not quite um, a parabola or an x to the third in here, because we know as this goes up forever, it also goes this way forever. And ours, it won't go this way forever. We're bounded. Okay, so now let's think about some shapes. Can I do this one? Not if I want to hit that point. Can I do this one? Well, sure, except did we have two x-intercepts? No, we did not. So what is of option to us? Well, it is possible in some cases that we could have this, but that's kind of rare and it requires a bounce there. And so I would need an x squared there to get that bounce, two of the same x-intercept. Actually, I would want that. That's going to give me that double root so that I come down, I believe. So instead, what is it that happens? Well, and there we have our shape. Now, I don't necessarily know that it's that shape for sure, but if this is -2 and this is -1, all I need to do is plug in a value between -2 and -1 and see if my point lands here or down here to confirm that. So if I plug in a -3/2, on top I have a -1/2. -3/2 times -3/2 is 9/4 minus 16/4. And look what I'm going to have. I'm going to have 9 minus 16, or -7/4. I'm less concerned about what the value is at this place, but I see here a negative divided by a negative, and that's why I've got a positive. You could certainly take this and divide it by this, and you'd have flip and multiply 2 7ths -3/2. Talk about leaving some space. 2 7ths. Okay, so that's great. We've got what's in between. We're not afraid to use a test point if we're unsure of the shape, but really, we have to be taking one of those shapes in there. All right, now, what about over here, and what about over here? Well, again, I'm going to use a test point to figure out if my graph goes like this, or if my graph goes like this. If I plug in a 3 here, 3 plus 1 is 4. If I plug in a 3 here, 9 minus 4 is 5. And that's positive, so we're above the horizontal asymptote. Please don't forget to label that point 4/5. Now, what about over here? Well, let's repeat the process with -3. -3 plus 1 is -2. -3 squared is still +9. Minus 4 is still +5. So if I plug my -3 here, I have -2/5. A negative number is definitely below 0. My point is going to be here, -3, -2/5, and I'm going to bend to my asymptotes. Okay? And no, we didn't have this x-intercept. So I say we should probably practice one of those again, now that we've seen it. I'll do this next one, and it would be great if, you did the one after that. So here's the next one. Y equals x squared minus 7x plus 6 over x squared minus 4. Hey, by the way, if you want to try this one too, you could just pause the video right now. Yeah? All right. Give it a pause. Come back when you're done. So here's what I'm doing. I've got x minus 6 and x minus 1 on top, x minus 2 and x plus 2 on the bottom. So I see my x-intercepts inside his opposite land. Ooh, x-intercepts. I have more than one. You can have more than one x-intercept. You can have more than one vertical asymptote, but you can only ever have one y-intercept if you're looking at a function. Okay, so my x-intercepts occur at 1 and 6. My y-intercept, I cover up all the x's. I get 6 over -4, which is -3/2. Vertical asymptote, that comes from setting the denominator equal to 0, so I have plus and minus 2. And a horizontal asymptote. Well, look, the degrees are the same, right? They're squared and squared. And so I look at the leading coefficients. Y equals 1 over 1, which is y equals 1. So let's plot what we know. -2, +2. And what about these x-intercepts? Well, I've got one of them at 1 and one of them at 6. Okay. Do I know anything else? Horizontal asymptote at y equals 1, and y-intercept at -3/2. So 0, -3/2. And you could certainly draw a y-axis here. But, yeah, I'm just finding that really confusing. So, if you want, you can put it there, but I'm not going to put it there until I'm done. So what shape do we think we have between these vertical asymptotes? Again, it's not possible for this one to exist because it would require an extra x-intercept here. I don't have a third one. Can I do this shape? Not and catch that point. So what's left? Well, this one's a possibility, but I'm not seeing that factor squared, so no bounce. And if no bounce, then that's not going to be working for me. So really it's just going to be the one that looks like that x to the third graph. Now, over here at -3, I'm going to plug in a test point. You can plug that test point in here. I often find it's easier to take that value and plug it in here. -3 minus 6 is -9. -3 minus 1 is -4. -9 times -4 is 36. And what about on the bottom? -3 minus 2 is -5. And -3 plus 1 is -1. And I end up with +5. Now, 36 over 5 is 7 1/5. Is that above our horizontal asymptote at y equals 0? Or is that below our horizontal asymptote at y equals 0? I'm sorry, y equals 1. Well, since 7 1/5 is in fact bigger than 1, we know our point is here, -3 36/5, and so our graph is going to be up here. I will say that I can't have this one because I don't have another x-intercept over there, okay? And even though you know it can't be this for that reason, I still need you to do a test point. I need you to label something on each piece of the graph. And that test point confirms where my graph needs to be. Okay, look, I have to pass through this point. Now, I have to pass through this point, and I have to bend to that asymptote. So what about this? Could it be this situation? Well, yeah, that shape is not impossible, with the exception of, wouldn't I need another x-intercept? Well, I don't have another x-intercept. That's my only x-intercept to the right of 2, and so therefore I can't have this shape, which means my shape must be this shape. Now, look what's happening here. We are crossing and approaching that horizontal asymptote at y equals 1. All right, there's that one. Any questions? You should send them to me on GroupMe if you have them. Okay, let's go from there. Your turn, for sure. Will you please do this one? Y equals x plus 1 over x squared minus 5x plus 6. Pause the video, give this one a try. No, really, you really should. Because you're never going to own this stuff if you don't practice this stuff. Okay, I know that denominator factors. And so what do I have? Well, I've got an x-intercept at -1, because I set the top equal to 0. If I cover up all the x's, I end up with +1/6 for my y-intercept. And vertical asymptotes, we set these equal to 0. Inside is opposite line. X equals 2, x equals 3. And horizontal asymptote? Well, let's take a look. The degree of the top is 1. The degree of the bottom is 2. The degree of the top is smaller than the degree of the bottom. So we know y equals 0 is going to be our horizontal asymptote. Okay, so let's go. I've got a vertical asymptote at x equals 2 and another vertical asymptote at x equals 3. You know, you could draw them like this because you're so used to using that amount of space between numbers for hash marks, but now it's going to be really hard to draw and label that shape in here. So don't do that to yourself. I mean, really, it is self-punishment when you do that. Give it some space, spread it out, stop making the stupid hash marks, and just label things clearly. That's what we really need here. Okay, so I've got my vertical asymptotes. How about some x-intercepts? I have only one, and my x-intercept is over here at -1. And do I know anything else? I have a y-intercept at 1/6. I'm going to put -1 a little further. And my y-intercept at 1/6. Okay. So, horizontal asymptote, y equals 0. Do you see? Let's look over here first, not between. Oh, by the way, you're doing this one? Did you pause the video? Oh, pause the video. This is something for you to wrestle with. Okay, welcome back. So, this is us crossing the horizontal asymptote. Now, really, we're going to, right, we have to connect these dots and then bend to the asymptote. But when we come out the other side here, we're not going to go down forever. We have to approach the horizontal asymptote. So what's going to happen here is we're going to cross and come back like that. Okay? When does something like that happen? Well, that happens when the horizontal asymptote, that can happen when the horizontal asymptote is on the x-axis and the x-intercept is not between the two vertical asymptotes. So I get something like that. But what about here in between these two vertical asymptotes? Can I have this one? No, because that would need an x-intercept. And I don't have an x-intercept here. This was my only x-intercept. Could it be this shape? That's right. No, it can't because I don't have an x-intercept there. So I can't have that at all. So my only choices are, is it this shape or is it this shape? And how am I going to know? I'm going to use a test point. Something in between 2 and 3. I know. What about 2.5? So if I plug a 2.5 in here, 2.5 plus 1 is 3.5. Or, if you prefer, 7. And down here, 2.5 minus 2 is 1/2. 2.5 minus 3 is -1/2. And when I multiply these, I have -1/4. Now look what you got. You got a positive divided by a negative. That's going to be negative. If I do the flip and multiply, I'm going to be able to cancel out 2's, and I'm going to get -14. So my ordered pair here is -14. Oh yeah, just -14. And that's definitely below my horizontal asymptote. So this goes away, and this is the only thing I'm looking at. Well, what about over here? On this side, I've got either this one or this one. How do I know which? That's right. I've got to plug in a test point to know. So if I plug in a 4, I've got 5 on top. And if I plug in a 4, I've got 2 times 1 or 2. 5/2 is my y value. Can I be down here? No, these are all negative y values. So my point has to be up here at 4, 5/2. All right. Now, really, you need to practice this some more. And you should, and you can. There's an assignment for this. You could do them all. I kind of want to look at this one next. What happens when you do this one? Y equals 2x minus 9 over x squared minus 9. Well, I see two vertical asymptotes on the bottom, one x-intercept, so get to work. Show me what you got. Pause that video, give it a graph. Hey, welcome back, everyone. So my x-intercept, which comes from setting the top equal to 0, is 4 halves. And my y-intercept, which comes from setting x equal to 0, I get negative 9 over negative 9, which is positive 1. Why did I write that as a 2? Oh, that's a 9. 9 halves. Okay. Vertical asymptote, two of them. X equals plus or minus 3. And a horizontal asymptote, well, the degree of the top is 1, the degree of the bottom is 2. When the degree of the top is smaller than the degree of the bottom, then I know y equals 0. So let's draw what we know. We've got negative 2, we've got positive 2, we have an x-intercept at 4 and a half, or 9 halves. Our y-intercept is at positive 1. Wait, vertical asymptote. Sorry, my brain is still in the last problem. There we go. And this was 0, 1. Okay. So, in the middle, can it be that one? No, because I don't have an x-intercept over there. Can it be this one? No. Aside from being really bad and not quite getting to that asymptote, I don't have another x-intercept over there. Could it be this one? No. Now I need 2 extra x-intercepts, and I definitely don't have that. Could it be this one? No, because how could I get through that y-intercept? My only choice here is this one. Okay, we need to do some analysis here. We need to do some critical thinking. Now, over here, well, we know that there's a horizontal asymptote here at y equals 0. And so I've actually got two choices here. My graph could come up and then back down. Or my graph could come down and then back up. We know we have to end up by approaching the horizontal asymptote, and we have to pass through that x-intercept. The only thing I can do is test a point. Sometimes I find it convenient to test a point over here. Sometimes I find it convenient to test a point over here. I don't really care as well, as long as we're looking to the right of x equals 3, and either I want a number between these two numbers or to the right. This is 4.5, so I'm just going to plug in a 5. 10 minus 9 is 1, and 25 minus 9 is 16. I get 1/16. Is that a positive number or a negative number? It's a positive number, so I must be up here. 5, 1/16. And that's my graph. This does not exist. Okay? And then finally over here, again, I don't know if my graph should look like this, or if my graph should look like this, and the only way I'm going to find out is test a point. This is negative 3, so how about negative 4? Negative 4 times 2 is negative 8. Negative 8 minus 9 is negative 17. Negative 4 times negative 4 is positive 16. 16 minus 9 is 7. Well, look, negative 17 over 7. So this point here, not this point here. In order for me to have this graph, that test point would have had to give me positive 17 over 7. But instead at negative 4, I had negative 17 over 7. And so this goes away. Ta-da! Graph. All right. Now, remember how I said at the beginning, vertical asymptotes, and sometimes, you don't have them. So take a look at this one. We've got y equals 1 over x squared plus 1. Now this is a very interesting shape for us. When I set the top equal to 0, does 1 equal 0? No, it doesn't. There's no x-intercept. That's what that tells me. If I set x is equal to 0, I have 1 over 1, so I do have a y-intercept at 1. The degree of the top, well, this is x to the 0 here. The degree of the bottom is definitely bigger than the degree of the top. So I know y equals 0 is the horizontal asymptote. But what about the vertical asymptotes? Do you see? Right? X squared plus 1 equals 0. X squared equals negative 1. You take the square root. I'm not taking the square root of that. I'm not putting any imaginary numbers on our real number graphs. What does that mean? It means no vertical asymptote. Yeah, really. So let's graph what we have. We have a horizontal asymptote at y equals 0. We have a y-intercept at 0, 1. We have no x-intercepts and no vertical asymptotes. This is all I've got. I know. It's kind of like, now what, Kukla? Well, like this. Yeah, that's it. We're looking for a smooth curve, and we have to approach these horizontal asymptotes. Now, you could make an argument for this and this, but that pointy thing there, that's not something that, we only see pointy thing this year when we're talking about absolute value. So this is mine. Again, you can test some points. Let's test 1 and negative 1. If I plug a 1 in here, 1 squared is 1, 1 plus 1 is 2, 1 over 2. That's above y equals 0. And then if I plug in a negative 1, negative 1 squared is also 1, plus 1 is 2, 1 over 2. And yes, this is an even function. It does have y-axis symmetry, positive. And so my graph has to pass through that point and pass through that point. Okay? All right. So there you go. No vertical asymptotes. I think you should do one of those also. So here's yours. Y equals 3x minus 4 over x squared plus 4. Okay. Give it a try. Pause the video. Come back when you're done. Hey, everyone. Did you get x-intercept at 4 over 3 and a y-intercept at negative 1, because negative 4 over positive 4, because that's not a 9, that's a 4. Did you say that the horizontal asymptote was y equals 0 because the degree here, first, degree here, second, degree of the top is smaller than the degree of the bottom? And vertical asymptotes, yeah, I'm not taking the square root of negative 4, so none. Okay, so let's graph what we know. We know we have a y-intercept down here at negative 1. We know we have a horizontal asymptote here at y equals 0. We know we have an x-intercept over here at 4/3. And yes, it is okay to cross the horizontal asymptote with rational functions, not exponentials, but with rational functions, as long as we approach y equals 0 by, as x heads to infinity or as x heads to negative infinity. And so I know I'm going to be doing something like that, because I'm going to be shooting out of this point, but I got to come back up to this line. Now, what I don't know is, am I shooting out of this going like that? Or am I shooting out of here and going like that? But for our purposes, really, any of these is fine. I need to see going through that y-intercept, and I need to see approaching that horizontal asymptote. Okay, so what about on this end? Well, same thing, same time. I come out of here, and I'm tempted to want to go up forever, except there's this horizontal asymptote here. And so I have to come back down and approach it. Again, there's lots of ways I could do that. I could keep going and come down. I could make it very, very short and come down. And really, any of those are going to be considered the same for us. Okay? Okay. And there's our graph. We want to see approaching that horizontal asymptote of y equals 0. Nice. All right. The last thing I want to look at with you today is transformations. Now, we did have 1 over x as one of our reference graphs. And we know that this reference graph has a vertical asymptote at 0, horizontal asymptote at 0, and we know now the degree of the denominator is smaller than the degree of the numerator is smaller than the degree of the denominator, so we've got that y equals 0 there, and if we set the denominator equal to 0, lo and behold, our vertical asymptote is there. We also plotted some test points, 1, 1, and -1, -1, to get the graph's shape. So there's our reference graph. And now here's the thing. You can actually use transformations on this. So what if we have y equals 1 over x minus 3 plus 4? So if I want to think about this in terms of transformations, and trust me, I usually don't. I mean, I love transformations, but no, I don't think so. I mean, think about what's happening here. This is inside the function. It's inside that 1 over x function. This is outside. My graph is going to shift up 4. This graph is going to go up 4. So this asymptote, not going to be y equals 0, going to be y equals 4 now. This point, well, I move right 3 and up 4. 1 plus 3 is 4. 1 plus 4 is 5. My vertical asymptote, denominator equal to 0. I added 3 to all the x values, including this x value. So this now has to be 3. And over here, I'm adding 3 to the x's and adding 4 to the y's. So this one's going to be 2, and I'm adding 4, 3. So yeah, I can do that. I can even take it further and say, all right, I know I have horizontal asymptote at y equals 0 on my reference graph, and I have vertical asymptote at x equals 0, and I have these 2 points to apply transformations to. So we want to add 3 to all the x's. So plus 3, plus 3, plus 3. And over here, we want to add 4 to all the y's. Plus 4, plus 4, plus 4. And so now we have 4, 5, and 2, 3 as the points on our graph. We see that the horizontal asymptote is y equals 4, and the vertical asymptote is y equals 3. Y equals 4. Wait, x equals 3. Sorry about that. X equals 3. 4, 5 is here above this horizontal asymptote of y equals 4. So 4, 5. 5 is above 4. And so we've got this point here at 4, 5. And then we have this point at 2, which has to be to the left of 3 and positive 3. Well, if this is y equals 4, then 3 is going to be down here. 2, 3, and bend to the asymptotes. So yeah, I can use transformations. I don't like using transformations with these. I mean, maybe on really simple ones like this, I'm pro transformations, but not in general. No. What could I do if I want to do this problem the other way, the non-transformation-y way? Well, I have to make a common denominator, because our non-transformation-y way always has just that one fraction there. So I'm going to make a common denominator, which means multiplying by x minus 3 over x minus 3. So I've got 1 plus 4x minus 12 over common denominator, or 4x minus 11 over x minus 3. So I make a common denominator, and now I see my stuff. There's my x-intercept, 11 fourths. There's my y-intercept, 11 thirds. There's my vertical asymptote, And my horizontal asymptote, because the degrees are the same, I'm looking at the ratio of leading coefficients. HA, y equals 4. That's my VA. Okay, so I graph, and what do I know? Well, I've got y-intercept at 11/3, and I have an x-intercept at 11/4. I've got a vertical asymptote at 3, and I have a horizontal asymptote at 4. I connect my dots. I need a test point over here on the other side of 3. If I plug in a 4 into 4x minus 11 over x minus 3. If I plug in a 4, I'm going to have 16 minus 11, which is 5, and 4 minus 3 is 1, and there's that point that we were talking about. It would be up here, 4, 5. And we would look like that. This is the same graph, just using different information. I'm not keen to do either. I can definitely use transformations. I don't know. I will say this. Making that common denominator so it's in the other form, it does take longer. I'm not going to kid you. But a lot of people, they get stuck with trying to apply anything more than simple transformations. So I guess I'll say, if I have something like this, y equals 1 over x plus 4 minus 2, then sure, maybe I'll use transformations on that. But even this one, I just want to do that. I don't particularly care which method you use, but I would like you to graph this. And that'll be our last problem for the day. All right, welcome back. So, did you start off with 1, 1, -1, -1, and our horizontal asymptote of y equals 0, and our vertical asymptote of x equals 0. So these are our reference elements, and what do we need to do? Well, this is inside the function, so I'm going to subtract 4 from all the x's. And this is outside the function, and so I'm going to subtract 2 from all the y's. So what do I have now? Well, now I've got this ordered pair, -3, -1, and here, -5, -3. My horizontal asymptote is at y equals -2, and my vertical asymptote is at x equals -4. So let's plot what we know. I know there's a vertical asymptote at -4. I know there's a horizontal asymptote at -2. I know that I'm supposed to pass through the point -3, -1. So if that's -2, then -1 is about here, and -3 is to the right of this. So I've got this point here called -3, -1. And okay. Then I have this point. Oh, -5 is to the left of -4, and -3 is below -2. And so I've got this point over here called -5, -3. And that's pretty fast. Okay, so transformations, graphing rationals. I encourage you to practice these some more. You could always open up and start, breakout room problems, homework problems.